So, we were discussing last time the silicon on insulator analysis of that we are discussing, and I will just go a little bit back 1 or 2 slides. So, that because I had rushed a bit during my last lecture on that portion. So, we will just start from there 1 or 2 slides. Compared to the bulk MOSFET, there are different modes of operation in the case of SOI. So, that we have said you can have the front channel inverted all the time, but back channel can be either accumulated, depleted or inverted. So, that is 2 channels are there. Now, if I make this thickness very thin, thickness of the SOI layer T silicon very thin to nanometer scale, 10 nanometer, 20 nanometer of that order, then a phenomena called as the volume inversion takes place. Entire channel will be, both the inversion layers will be merging. That also we will discuss. Now, I just wanted to bring in some aspect of this depletion and accumulation. To make things clear, if you take a look at this bulk MOSFET, you can see the gate, red is oxide, the silicon will be depleted if I apply plus voltage to the gate, if this is p type. Okay. Depletion charge is negative in the p type substrate. So, this is the depletion plus voltage. If I keep on increasing, you know that you can invert the surface. When the surface potential is twice phi f, then you say it is inverted. So, I have shown the plot last time itself, I have discussed this. The voltage drop across the oxide leads to the electric field which is constant, then the electric field at the oxide and at the interface will be different. There will be discontinuity because the flux is continuous. Epsilon oxide into E oxide is epsilon silicon into E silicon. So, this field will be about 3 times smaller than that, because the permittivity of silicon is about 12, that of oxide is about 4. So, 12 by 4, that is the ratio is 3 times smaller. And if the doping is uniform, as it happens in most cases, the electric field is linearly falling. Okay? The electric field is linear, I do not have to derive that, because you already know it, that you recall that. And the slope of this depends upon the doping. Higher the doping, that will be steeper. Now, if you integrate this, you get the voltage. X, if you integrate it, is x square. So, if it is linear, that will be parabolic, the voltage. And if it is constant, when integrate it becomes a straight line. So, you have got the voltage drop. Field actually is V g minus V silicon divided by T oxide, that is the field there. So, V silicon is like this. Now, if it is inverted, it will be inverted when V silicon becomes twice phi f. Okay. So, that is depletion or inversion. Usually, you operate in this region. But if I apply negative voltage to the gate, bulk MOSFET, we are still on bulk MOSFET, black is the gate, then you have got this red oxide, then the silicon. Now, you can see when I apply minus here, the plus charges can be supplied very easily by this majority carriers in the p type region. So, they accumulate plus charges, they are mobile charges. Remember what you see on the left hand side here, when it is depleted, I put it inside a circle to show that it is not mobile. It is the dopant which has been depleted of the holes, whereas this is the plus charges which have accumulated there. Okay. And this is a charge sheet on that. So, whatever voltage you apply appears completely across the oxide. So, the field is actually equal to, or the voltage is minus V g here, and it is 0 just at this point. So, the voltage is linearly falling across the oxide, minus to plus, but that is 0 to minus V g. And the electric field of course, is constant, no charge within the oxide. So, V g divided by T oxide will give you the electric field. Okay. So, this is a chart sheet. Now, when you go to the SOI MOSFET, you have got the front gate which almost looks like this. I have shown the MOSFET source drain also here. Here I can put a source and drain here, if I want invert and current carriers. Here I have plus here, minus here. This is a schematic diagram. Front gate metal or polysilicon doped, red color is the front gate oxide. This is the SOI layer P of thickness T silicon, and this is the back oxide. So, here you have got front gate and you also have got the back gate. Okay. So, front gate oxide, back gate oxide. Now, you can invert the front gate by applying sufficient gate voltage. At the same time, you can have the back channel accumulation, depletion or inversion. You can accumulate it by applying a BGB negative, like what you saw here. If I apply negative voltage here, it will be accumulated. If I apply plus voltage to the back, I can deplete it from the back side. If I apply large voltage, I can invert it. That portion we will see now. So, this is the structure which I did not show in my previous lecture for the analysis. So, you can see now here, whatever we have discussed yesterday is here or previous class, that is this diagram is redrawn here, voltage, that is the bulk MOSFET. Now, let us see this back channel is accumulated case. Okay. So, this we have discussed yesterday. What you do is apply a negative voltage to the back gate, apply negative voltage to the back gate. So, there will be plus charges here. Now, if I apply plus voltage to the gate with respect to the source or with respect to the substrate, which is somewhere it is a cross section on the surface, you will have a contact you can put outside this gate region. Otherwise, you can apply voltage between these two also. So, if I apply voltage, then this will start depleting, completely depleted, and once it depletes, the additional field lines will cross this and go into the other side. That is what we discussed already. So, you get this is the situation when it has just got depleted, dotted line. I have got actually plus charges here on this side. Okay. On the surface, you have got plus charges, exactly same way you have got here. You have got the plus charges here. That is giving rise to the field here. So, after this depletion, if I increase the voltage, the field lines will cross this and the entire field will go up. This portion I think I have discussed this. This is not a very important need for the SOI MOSFET, but I just showed you, you can get inversion here, and you can, because you have applied a plus minus voltage here, the voltage is 0 here. Because if you recall here, the potential where this accumulated is 0. Okay. So, you have got 0 potential here, surface is inverted here, and the electric field will depends upon twice phi of minus 0 divided by T silicon, that is the average field. Okay. If this were completely insulated layer, then twice phi of minus 0 divided by T silicon would have been flat. Okay. Now, what happens is, you have got this particular field present here already. So, you superimpose that whatever voltage field was there, you superimpose on that. Original field was like this varying. Now, beyond that, a constant field from here, here, they both are same. This gets lifted up by the amount, that is additional field. Okay. So, you can actually find out how much this field is. How do you find out? Twice phi f divided by T silicon is an average field. Okay. So, it is an average field. Say for example, okay. For example, if I just draw this like this, I have when this is the silicon, this is the silicon, I have the oxide on either side. Now, and it is just depleted, it is like this. Lines are not straight actually, it is not coming like straight. So, if I draw it here like this, okay. Now, if I take twice phi of minus 0 and take the average field, that is like this. This is ESF, this is backside field. So, average field is that. Now, what I want to find is, so I know this is actually equal to twice phi f divided by T silicon, average field. So, voltage drop is that. But now, I want to find out how much is this quantity is. That quantity is because this whole thing has got shifted up. So, whatever I have here is half of that. If the whole thing is shifted up, I get that like this. Now, this quantity is the same as half of that. Okay? Average is between these two is midline. Here it is maximum is 1 and 0. So, what is this quantity? What is the field here? When it is just depleted, whatever charge is there in silicon divided by epsilon s, that is the electric field here. So, half of that is that. So, if I have this quantity as twice phi by T of T s, that is the field here, this quantity is that is that. So, this is the ESF. So, I know how much is the field here is, that is ESF. I am writing is bad, surface, front surface. Okay. So, that is the ESF from here to here total. So, that is why you find out average field, add to that. So, whatever distribution you have, all that you do is, supposing I have a potential difference like this is phi f and this is phi s, phi back. Okay. Okay. If that is phi b backside. Now, this minus that divided T of s is the average field. This may not be equal, let me just do it once again. I remove that and I go back to this and oh my god. Okay. So, you have got, let us say this is phi b back channel. This minus that divided by T of s is the average field. To that, because that there if I take the electric field, it will be like this. So, the average field is whatever I get, this minus that divided by T of s. In this case, it was twice phi f only because this voltage was 0. Here it will be some phi b is there. So, I find out the average, phi f minus phi b divided by T of s is that average field, and what is that quantity? That is half of this, that is the same as this. So, this is a general case. So, if you understand that, there is nothing more to, no more difficulties will be there. So, I just go back to this. Okay. So, here you have got that electric field like that. This field is actually twice phi by T of s plus whatever field is there, half of that you add to that, that you will get that. Okay. Now, let us go to more realistic situations. So, you can see I changed the whole situation now. This was back channel was biased with negatively. So, you have got accumulation layer here. More practical situation. I have the back gate grounded. This is where I think we started last time and some understanding needed for bit more analysis. So, I apply plus voltage to this. We are finding a situation where the front channel is inverted, back channel is, we do not apply to the back gate. So, it will be depleted. What happens? When I apply voltage, plus voltage to this front gate, okay, this is grounded. This is with respect to that you are applying. This is connected to the ground somewhere, substrate somewhere else. You are not able to see in the cross section. So, I am applying voltage across that. So, you see at a particular voltage, as you keep on increasing, the depletion layer keeps on moving. Okay, I will just go back to this now. Okay. So, let us see whether I can do this. Okay. So, what we are trying to see is the if I have the layer like that, silicon, T silicon. Now, if I apply plus voltage to the gate, plus here, I have grounded this. This is the back oxide, this is oxide. So, what happens is the moment you apply voltage, there is a depletion layer formed, that is depleted. They are all negative charges, immobile. Keep on applying, increasing the voltage, this keeps on moving, ultimately this merges with that. So, when it just reaches this point, that is called punch through. The entire depletion, the silicon layer is punched through. So, then what you will get will be, I will just show that at that punch through, you will have the, I will just remove this particular thing. Okay. So, I will go back to this, back to this. Just when it is punched through, electric field will be something like this. That is 0. 0 electric field here. This is the maximum field. Okay. What happened? Okay. So, you have got the electric field like that, and you know at this point the electric field is Q s by epsilon s. Total charge, what is Q of s? Q n a T of s by T of s, that is the charge. That divided by epsilon s is the field here, like before. Okay. Now, if I increase the field voltage further, beyond punch through, what happens? There is no charge here, there is no charge here, there is no charge in the oxide, this is oxide. That is oxide. Okay. I hope you can read that. There is an oxide there. So, if I increase further, additional field lines will cross here, additional field lines will cross there, and whatever additional field lines there is no charges here, it will be down by factor 3. The oxide, field oxide divided by 3 is a charge here, field. So, here if this has gone up, this will go up by the same amount, but by factor 3. Now, whatever electric field has increased here, everywhere it will increase, because there is no charge there, or whatever field line originates from there terminates there. And once it reaches here, there are no charges in the oxide. So, what will happen? It will cross the oxide, but the electric field here in the oxide, okay, will be higher, like the electric field here. The field here will be higher by factor 3. So, you can see the electric field distribution will be like this now. Now, I can find out this is the electric field at the surface, ESF. Why are we finding electric field at surface? If I know the electric field at the surface, I can find out what is the voltage drop across the oxide is, because voltage drop across the oxide is ESF into epsilon s, that is the total charge beyond that point, divided by C oxide F, charge by C oxide F. Charge is ESF into epsilon s divided by C oxide F will voltage drop. Now, when you go into this situation, go back to the diagram now. So, I hope it is clear enough now. So, what we are trying to find out is how much is this field. The ultimate goal is to find out how much is the surface field. When the surface potential is, if you take a look at the surface potential, I think I have that here. If I take a look at surface potential, see this is the dotted line is the electric field when I just depleted it, okay, that particular thing. Now, when I increase the voltage, the field has gone up, the entire thing has gone up, the diagram which I have drawn. I put ESFD to tell you that the back channel is depleted. Front field, surface field, when the back surface is depleted. Okay. So, how much is the field here? How do you find out? What is the potential here? Psi SF. Because the field lines are crossing this oxide and because this is grounded, there is a drop across the oxide. So, the potential here is plus, channel potential on the back surface is plus with respect to back gate. So, that is Psi SB positive. So, the voltage difference between the front channel and the back channel is Psi SF minus Psi SB. I am trying to find out how much will be the threshold voltage of the front gate. At threshold voltage, Psi SF will be twice Phi F. I have kept on increasing the voltage till this has reached twice Phi F. There is some voltage here with respect to ground, Psi SB. Okay. So, what is the ESF? How do you find out? Psi SF minus Psi SB divided by T of S. You can see that that is smaller than what you got in the previous case. Previous case, it was Psi SF minus 0 divided by T S, average field. To that average field, you add half of this field, Q S by twice epsilon S. Okay. So, here twice Phi F minus some voltage divided by T of S will be smaller average field compared to back channel accumulated. So, if I want to find out how much is this average field plus half of this quantity. So, I will get in this case also I will get in this case ESF will be twice Phi F minus Psi of S B divided by T of S, that is average field. Okay. Now, let me just remove that thing. So, plus this average field plus what will be the thing? Half of this. This is just when it had punched through, Q S divided by epsilon S is total field. So, this is the key situation. So, electric field is that. So, once you know this, multiplied by epsilon S, that is charge beyond that point. We do not know where it is all. We know this field, how to calculate, multiplied by epsilon S gives me the charge divided by C oxide F gives me voltage drop. So, threshold voltage at this point is, go back to that, threshold voltage at this point is actually equal to twice Phi F. We know that immersion condition, twice Phi F, voltage drop across that is twice Phi F minus Phi S B divided by T of S plus half of this field, okay, into epsilon S divided by C ox F. So, whatever we are telling Q substrate, that has got a bigger expression like this. This whole thing is there. So, instead of Q, only this charge is there, but there is charge coming on the other cat also. Whole thing is taken into account by this. That is the beauty of this using this surface potential. That into epsilon S divided by C ox F is the voltage drop. Okay. So, that is about the back gate depleted. Now, let us go and see the situation when I see here. Here the back surface potential is ISB, because this is grounded, there is a drop across the oxide. Now, I will take a situation where I deliberately apply voltage to the back gate plus, okay, that is, instead of making 0, I apply plus here, plus there. So, I keep the voltage plus here, and this green color that I have shown is the depleted region due to the back gate. See, I am applying that with respect to that is with respect to the substrate which is connected to this. So, you have got this is the depletion layer here, okay, up to this point. Now, I start applying front gate voltage with respect to this, that is substrate. What happens? as I keep on applying the voltage, I am not disturbing this, I fix that at VGB. Okay. This may be thick oxide, it is not inverted, because to invert depletion layer width is much more than the thickness, it is a fully depleted case. So, I start applying the voltage, just like in the previous case, you will have the similar situation where where that situation is slightly different now. Okay. So, the situation now is if you see, it is like this. This is the back channel, this is the oxide and this is the oxide, and part of it, that portion is already depleted, because I have applied plus voltage here. So, this field lines are like this in this direction here. Now, I come from this side. As I keep increasing VGF, what happens? This oxide, straight away there is some voltage drop across oxide, that is electric field. If I increase the voltage, what happens? That goes up, this goes up. At a particular point, I have this coming and that coming like that. Now, at this point, you see this is the T silicon. Part of this T silicon has been, depletion layer has been occupied by this backgate VGB. This has been taken over by that. You have fixed that. Now, when I have applied up to this point, you have got 0 field here, because if you plot these electric field lines from the left hand side and right hand side, okay, if you draw that was the depletion layer, which is already occupied by the back channel. Now, if I take the electric field now, how is it? Only here in the channel region, T of S. Over here, just 1 minute. Up to this point, depletion electric field is from right hand side, from here left hand side. So, electric field comes down like this. Okay. I think I better take a different color for that. That is like that, electric field. And if I take the electric field from here, that is like this, because of the backgate bias. So, that is plus higher here, 0 here. So, you have got a region where the electric field is 0. So, if I take the potential here, how will that be? Here it is actually potential, the potential here will be 0. It will come from here, I think I just change that. Okay. So, the voltage will come like this, corresponding to that point there will be 0, and from this side it will come like this, but this potential is smaller, okay, depending upon what was the gate oxide thickness, what was the backgate bias. So, this is the point at which 0. So, that is the situation you have got here. Now, at this point, what is the, it is not inverted here, it's the surface potential is not twice 5. So, I have to increase the voltage further. So, what I do at this point is, I will go back to that slide, it contains all the things. So, that is the situation that you have got. What I have drawn there is this situation, the bottom line. Okay. So, you have got it like this. Now, see this is VGF1 and this is VGB1. So, this portion belongs to the back gate, this portion belongs to the front gate. Electric field lines, you see, as I went on doing like this, here I have drawn it like this. See, instead of drawing it like this, instead of drawing it up like that, this is in this direction, that is in that direction. So, what we do is, we take it like this, draw the 0 line and draw like this. Instead of taking it up, we draw it like this, negative. So, that is what is done there. Okay. So, you have got that continuously there, implying that this is 0 here, this is negative here, because field is in that direction. So, this is the situation where what you have got here. Now, from here onwards, what I do is, I increase the front gate voltage by some voltage V, back gate by voltage V. See that there is no charge in between, completely depleted. The entire layer is depleted. All that you have done is now you increase this by same amount. The difference between the two voltages is not changing. That means, the electric field will remain same way. Okay? The electric field distribution here will not change. Where has that extra voltage gone? That is the thing. When I apply like that, okay, see here, if I once we have depleted completely, and this was VGF1 and this was also biased positively, beyond that point, just when it is fully depleted, beyond that point I increase both of them by the same amount V. That extra V does not appear here, the difference is same, but that extra V appears across with respect to ground, that is here. So, that this point becomes plus with respect to that. That is, the source junction gets forward bias by that extent. So, if this is forward bias, from that point on to the surface, whatever drop was there is present. See, from here to the midpoint there is some drop. Okay. When this situation, see, from here surface to this point there is a drop. Now, if I increase this by V, this potential here also has increased by V. That means, the source junction has got by forward bias by that V extra here. But here, what is the forward bias voltage? Whatever V is there plus whatever originally was there. There is a potential here. See, when the point, just when it has depleted here, potential here is 0. This, what we are plotting is just outside the surface here. That was 0, it was rising to that phi S1. But now it has gone up here, this has gone up here. So, you can keep on increasing it, so that this is inverted, this becomes twice phi f. But this should not have been inverted, because that depletion layer is narrower here. Supposing you had applied voltage, so that the entire thing is at the middle, both would be the same potential, it will be both will be inverted. So, that is the situation that you have got. Okay. So, now let us see. So, here in this case, what will be the field now? Psi SF minus psi SP divided by T silicon, that is the average field, that is the field there. Psi SF minus psi SB divided by that is the average field. Now, okay, if I want to find out how much is this field, what do I do? Q s by twice epsilon I add. And how do I find out this one? Q s by twice epsilon and subtract, that is all. So, it is, you can get the whole thing by solving a Poisson's equation, but you can see this is very easily you can see for any bias condition. Okay. So, this will be inverted, this is depleted. Okay. Now, you have got a situation where I have applied a, let us say this is a situation where need not be oxide, need not be the same thickness, but I can apply a large enough voltage, so that the depletion layer from back side comes up to the center. So, now I can come from the front gate till the depletion layer merge, that is the situation. So, if the depletion layer were coming up to this point, the potential will be symmetric. Even for thicker back gate I can do that, but the difference will be the back gate voltage will be more, because more voltage drop will in the oxide. So, here the drop here from the midpoint to the surface and from midpoint to surface both are equal, but for the same field the voltage drop here will be something, here will be more. Now, beyond this point I increase both the voltages by an amount equal to V, till that goes to twice phi f. Because it was symmetric originally, when it is depleted, when you started applying the voltage, this also be twice phi f. So, what is average field here? 0. This minus that is 0. So, average field is 0. So, the average field is 0, but the field here will be how much? The average field is 0. The field here will be this minus this by twice T s, the 0, plus Q s by twice epsilon. That is the field there. Okay. So, you can see that Q s is actually, what is Q s? Charge in the depleted region, Q n A T of s. So, if I use lower and lower doping, Q s by twice epsilon, that is, this field will be smaller. If this field is smaller, this field also will be smaller. You can see now, we are seeing it like this, but in the device you are able to reduce the doping here and also reduce the thickness here, the field here will be reduced. If the field there is reduced, the electric field there also is reduced. That means the voltage drop across oxide will be reduced. That means your threshold voltage will be lower in this case. When I got into twice phi f here, the voltage drop was less here, correspondingly voltage drop here will be less, because field is less. If this field is less, this is less, drop is less. So, what we are telling is, you can have low electric fields in this direction, which we are looking forward to for increasing the mobility. So, electric field in this particular direction, this transverse direction will be reduced by reducing the doping, by reducing the thickness. Okay. Now, you may question, if I reduce the doping, will I have a short channel effect? That aspect we will address later. The difference between the bulk MOSFET and this is, you can make it thinner and thinner. Okay. You can make it thinner and thinner, so that these two have more tighter control on the channel. If the thickness is small, if I have the drain here, if this is long compared to this thickness, this has a better control, gate has a better control. It is like two regions. Okay. See, if I have the gate here and if the drain is here, source here, okay. I have the oxide here, I have the oxide here. Suppose it is thick, okay, this may have control over here, this point. Supposing you make it very thin, this is the source drain. Suppose it is very thin, this has a better say on this region than this region. So, the gate will have more control over this region here than that region. So, you will be able to go to much shorter channel lengths and you will be able to reduce the doping, because this region is controlled mostly by this gate. Even if the doping is reduced, the drain depletion layer is not able to encroach into the channel. Okay. So, that is the situation. You can we will see more details of that later, but right now what we are saying is thinner silicon, more lightly doped, fields in that direction will be less. You will be able to invert, because of that we are at a lower voltage. Okay. Now, a most general case. Now, since you understood the whole thing, we will analyze the situation. VGF is applied, VGB is applied there. I am showing only the front oxide, back oxide and this channel. Gate is here, gate is here. Okay. And I have got a situation where electric field is across oxide is there, across the silicon is like this, and across oxide. This situation is there when you have got electric field is in that direction, electric field in this direction. So, you can see 0 is here. It is general case. So, we already discussed this now in the previous slides. So, what is electric field here? I am just arbitrarily drawn the electric field like that, but how much is the slope here depends upon the doping. Electric field doping, this slope depends upon, as you start depleting, you can see slope depends upon doping. If it is very lightly doped, it will be flat. If it is very highly doped, it is going like that. So, I have drawn this diagram here to calculate how much will be the threshold or what is the gate voltage applied to this for this situation. General case. The gate voltage at the front gate is actually equal to oxide drop Vx(f), V oxide front gate plus whatever potential is here, psi Sf. See, this is a potential Vgf, psi Sf, psi Sb, Vgb, all with respect to ground point, all with respect to this ground point. Okay. So, we are drawing that diagram here. I wish I had this diagram here also, but it is okay now. So, what is this field? Now, you know how to find out psi Sf minus psi Sb divided by T silicon is the average field plus Qs by twice epsilon s is that field. Okay. That is the ESF. Exactly the same way we have argued out difference between the potential divided by silicon thickness gives the average field, the dotted line. I add that half of that Qs by twice epsilon s, that is that. Qs is that quantity. Now, what is the voltage drop? Voltage drop is whatever field is there into epsilon s, that represents the charge beyond that point, divided by C ox f. Okay. So, I just substitute this here, epsilon s by C ox f into that quantity, whole thing. So, that is this quantity, just a substitution. Put this here, substitute that here, you get that. Now, using this equation 3 along with that, I will get what is front gate voltage is. Okay. We are now not saying whether back gate is accumulated, depleted or, but we know that field distribution is like this. So, front gate voltage is actually this quantity plus psi Sf. See, this quantity, the potential here is whatever potential here, psi Sf plus that oxide voltage drop. So, add to this quantity this psi Sf. When you add that, this all this equation. There is nothing new here, just I am adding this, putting it in this form. Only thing that I have made is epsilon s by T of s is actually the capacitance of this silicon layer when it is fully depleted. Instead of writing epsilon s by T of s all the time, like epsilon oxide by T oxide, you say the C oxide. Epsilon silicon by T silicon is C silicon. That is the meaning of that. So, you replace that by Cs, so you will get this equation. Same way, I can write, it becomes very simple now. So, if you are able to write this equation by drawing this diagram, which you can do now, you can write for this back gate also. All that you do is, you have to write field here is that minus this quantity, average minus that quantity. When you do that, you get Vgb is equal to, in terms of the psi Sb, you get this. Replace C ox f by C ox b. When you want to go to back oxide, it's symmetric equation. Psi s f by psi Sb, C ox f by C ox b, Cs remains Cs, psi Sb by psi Sf, all ulta or reverse. Okay. C ox f by C ox b. So, that you can now deal with a situation whichever channel is accumulated, whichever channel is depleted. So, here you can see from here how can I get the, I want to see, this is a general equation. I want to find out the threshold voltage when the back channel is accumulated. What do I do here? Front channel is inverted, psi Sf will be substitute twice phi f. Back channel is 0 when it is accumulated. It is not really 0, slightly negative, but we are putting it very close to 0, 25 millivolts, 50 millivolts of that order. So, I remove these. So, then threshold voltage will be 1 plus Cs by C ox f plus twice phi f plus that quantity. When the back channel is depleted, I will have twice phi f and psi sp here, pi sp here. When the back channel is inverted, what will I get? How do you do from the same equation? Back channel inverted, front channel accumulated. Substitute twice phi f here, here twice phi f, psi s b also twice phi f. Both channels are inverted, then both are psi s b. Then you can see this term and this term cancel out, and you will have twice phi f plus q s by twice e oxide f. With psi s f is twice phi f. Okay, I will have written that thing here. See, back channel accumulated, you get that substitute when you substitute in that equation. If you go back to that, you will see that all that I did is put this 0, then you get that equation. Middle term is 0. And when the back channel is depleted, more or less it will be that twice phi f plus q s by c oxide. But some more terms will come, but approximately it will be this. Both channels are inverted. These two terms are cancelled because both are twice phi f. You will have only this term, which is twice phi f plus that term. So, you can see, compared to these things, back channel accumulated, back channel depleted, both channel inverted. Here only front channel is inverted. When I see these symbols are threshold voltage of the front channel with the back channel accumulated, threshold voltage of the front channel with the back channel depleted, threshold voltage of the front channel, back channel inverted, both are inverted. So, if the back channel is accumulated, you can see threshold voltage is highest. In the case of bulk MOSFET, if you recall, threshold voltage is this twice phi f plus q depletion by C oxide. So, you can see this twice phi f gets multiplied by a big factor here. So, threshold voltage in the accumulation condition will be much more than even the bulk MOSFET. So, that will not work out for you if you are looking for reducing the threshold voltage. This one, in the bulk MOSFET, it looks like almost like a bulk MOSFET, twice phi f plus q d by C oxide. But in the case of bulk MOSFET, what is the q d? If you see the bulk MOSFET, MOS, that is the V threshold voltage is twice phi f plus q d by C oxide. Let us say a situation where the oxide thickness are same. Now, in the case of fully depleted also, that is V T f fully depleted, we saw twice phi f plus q s by C oxide twice. Okay. Is that right? So, you have got that particular situation now. So, here differentiate these two terms. Q d in the bulk MOSFET is Q n a x t maximum at twice phi f. Here this is Q n a into T of s. T of s is much small compared to x t. So, this is much smaller compared to Q d. So, this will be V threshold voltage of the bulk MOSFET will be greater than V threshold voltage of that. Now, when you go to inverted case, you have got V T f, back channel also inverted, that was equal to twice phi f plus Q s. Sorry. Okay. That's good. In fact, if you go, I think I made a mistake there. In the previous case, it is not there, 2 is not there. Okay. But when you go to this now, you have got this twice. This is much smaller compared to the bulk MOSFET, maybe half, 1/4 or even smaller than that, depending upon how thickness you reduce, divided by twice phi f s, okay, twice epsilon s. Am I correct? So, this is a term which actually gives rise to voltage drop across oxide. So, in all the cases what you are doing is, by taking this situation, what you are doing is, okay, see here, in this case the drop across the oxide is small because of depletion layer charge is small. Now, if you reduce the doping, this further can be reduced. Ultimately, you can get the threshold voltage equal to twice of itself. Okay, very small drop in the oxide before inversion, just when it is inverting. Okay. So, now if you see the electric fields, psi s b 0, you see this equation, or all the cases this holds good, psi s f minus psi s b by T silicon plus that half of that, this average field plus this. So, in psi s b 0, that is that field, and psi s f, psi s b is greater than 0, this term is practically same thing, or even if some factor is there, this is there, the difference reduces that term. When I go to back channel inverted, both are twice phi f, that is the field. Okay. Field in silicon. So, field in oxide is Q s divided by whatever is the epsilon s into divided by C oxide f. Okay. Whatever charge E s electric field is there into epsilon s divided by C ox f, that is the voltage drop. Okay. So, what we are telling is the field is smallest when the both channels are inverted, higher in this case, highest in that case. Okay. In the bulk it will be even higher, because you have to take care of the depletion layer which is wide. Okay. Now, this is the plots which you can see now. Electric field is highest there in the case of back channel accumulated, and the whole thing comes down, to this electric field is lower and the back channel is depleted, and you can see that the average field is here corresponding to this field is much lower when the both the channels are inverted. This sort of diagrams you will see everywhere, it keeps on lower, lowest when it's both are inverted. Now, you have seen the potential distribution twice phi f. If back channel is accumulated, potential is 0 here, the back channel is depleted, potential is positive here, the minimum is somewhere in between. When the both channels are inverted, that is twice phi f, and it is 0 or is minimum at the center, because half of this belongs to the front gate, half of this belongs to back gate. Okay. So, threshold voltage lowest in this case, higher in this case, higher in this case. Okay. Now, what we are summing up in this case is that you can go to lower threshold voltage with the fully depleted channel if both the channels are inverted, and you can make a symmetric gate, symmetric MOSFET. What is symmetric MOSFET? Front oxide, back, that is about like this, back oxide thickness and front oxide thickness same, everything same. I can connect them together. I can have a situation where I have the back oxide, everything is same thing, and front half governed by that. I can connect the back gate and front gate and back gate to the same voltage. Now, what happens if I do that? When I start applying the voltage from 0, what happens? Depletion layer starts coming from here, oh sorry, I think I have to, that will come like that. Okay. That is how it comes, and from here same way, that is how it comes, electric field. that is edge of depletion here. At a particular point, come like this. So, whole thing is depleted, and you have the situation where the potential is like this. That is the voltage across the silicon. So, both are same surface potential. Now, we raise the both are connected together. So, both move like that. After that, if I increase beyond that point, you see difference is not there. Okay. Then afterwards, it keeps on moving up like this till I get twice phi of all that. That is a double gate MOSFET, symmetric. So, people are looking into devices which are actually realized like this. Both gates connected together, and so that one gate control, because after all you do not want to have one supply for the front gate and one supply for back gate, make it symmetric, connected together. There are some issues that we will see when you sort out by some other methods. Okay. Now, let us go further down. So, you have seen that if you want to see the threshold voltage versus backgate bias, backgate accumulator threshold is higher, backgate inverter threshold is down, in between somewhere it is falling. Okay. This is just for completeness sake I have plotted. You can control that thing. How much is the slope will depend upon the ratio of the oxide thickness front and back. If they are equal, it will come steeply down like this. If the back oxide is thicker, it will come like that. Okay. You can analyze yourself sitting down based on whatever we have discussed now, it will be like this. And the difference between the front threshold voltage when the back channel is accumulated and when it is inverted is that Cs by C oxide F into twice phi F. That is the difference. You can see it by substituting in those equations here, this minus that is this quantity. That is it. Okay. Now, that means you can have the transfer characteristic for this MOSFET. I can take the characteristics in the back. Now, I am not showing a symmetric gate, we will come back to that afterwards. This is one of those experiments which some of our students in IIT Madras had done it, fabricated these devices, and you can see back gate is thick, maybe about 0.4 microns, and T silicon is about 87 nanometers, fully depleted, something like 10 to the 14 doping. Front gate oxide is thin, okay, something like maybe 0.1 micron or so, and W by L ratio is 200 by 15. L is 15 micron, long channel. We do not want to be bogged down by the short channel effect. So, transfer characteristic is exactly like the bulk MOSFET. The only thing is you can change from the accumulation negative, you keep on doing that, you can see threshold voltage becomes less like that. And if you go keep the back gate voltage all the time inverted large voltage, you will not be able to turn off by the front gate. So, these are just to illustrate that, and also you will get. Now, let us go to this particular situation. This is just for showing that you can have a good control of the back gate. You can change the threshold voltage drastically by using that. Unlike in the case of bulk MOSFET, you can bias the substrate, but if you can't apply forward bias onto that, because the source junction will conduct substrate current will flow. Okay, now, what happens to the subthreshold slope? Okay, that is what we want to see. Maybe I think I will take on this particular interesting thing in the next class. So, in summary, what we have said is that you can get complete control of the backgate bias, you can go from accumulation to inversion back channel, and you can have the threshold voltage varying like that. In fact, you will see that you can get also control on subthreshold voltage by using this quantity. And this is the main advantage of this is threshold voltage can be reduced, the transverse field can be reduced drastically, so that there is a chance for you to get higher mobility. We will continue on this from here onwards. The life will be much more easier, because we understand how it works out now, not much of mathematics from here, but more of what happens in those short channel devices. We will discuss that in the next one lecture before we wind up the SOI thing.